All right, well, you've just submitted homework assignment number 2. That one was a little bit lengthy, and so this next one, just to change gears slightly, homework 3, if I remember correctly, it only has 4 problems, and it's due on Wednesday. And so a quicker turnaround for this one, but it's a shorter duration assignment. So you know, that's how sometimes we roll. Sometimes it's a short assignment and I want it quick. Other times you get a little bit of extra time, but there's a greater number of problems. So we're going to be talking about gradients today, and you'll need to understand gradients to complete homework number 3. But after today's class meeting, you can definitely get started on homework 3, and it's posted on Blackboard now. So I'd encourage you to get an early start, spend some of that good weekend time looking at gradients. Okay, a couple of other announcements. One is that if you get sick of being at home, then consider taking some of your virtual classes on campus. You know, even if it's not an in-person or face-to-face class, you're still welcome to be on campus, and there are a couple of different places you can do that. At the library, they have learning hubs where you can make a reservation in advance, although I think probably there are spaces available on a walk-in basis. Same thing over in East Hall, although East Hall also has some snacks and kind of a lounge area set up, so you can take your classes there and also socialize a little bit. And then, of course, our engineering complex building is mostly empty during the week. The only time it's a little bit busy around here is Wednesday evening when some of the graduate courses are. So you are more than welcome to stop by the engineering building and, you know, take your classes here and maybe feel more connected to the university. And Cameron validates that the library is not full. So come on down.
4th floor is the way to go.
4th floor, nice and quiet up there, right? The other announcement that I want to draw your attention to is that the Division of Highways has a big and really well organized co-op program that's been going on for a number of years, and it's a great opportunity for students to get some professional work experience and make money during the summer. And they will take people after their freshman year. And so I think everybody in this class is past their freshman year and, you know, would be eligible from the standpoint of having completed enough degree hours. Division of Highways is taking people from engineering, also IT, and others as well. And so if you're in safety technology, they may have some spots available having to do with you know, highway safety and so on. The deadline is next Friday. You have to submit your application packet and accompanying forms by 4 o'clock next Friday. And if you're interested, I've distributed the application packet to the civil engineering students twice by mail already, but I recognize some of you aren't civil engineering students, and I think that DOH does take mechanical and electrical. You know, they'll find something to do for just about everyone. So if you want more details, you can just do a Google search of WVDOH Summer Co-op, and it'll take you to the link where this application packet is, or contact me and I'll send you the application packet. I don't have all the details about it, but I can point you to the person in Human Resources who does. Brett mentions that he worked last year and it was really good. I'm glad to hear that. I appreciate the confirmation and the testimonial there. If you want to have a good job prospects when you graduate, a great way to help ensure that is to show that you're employable during the summer. Cameron also did it and said it was a good experience. And so, you know, there are class opportunities during the summer, and there are co-op opportunities during the summer, and you can sometimes do both. You can do the co-op during the day and maybe take an online class if you need to get a few more credit hours over the summer. So just wanted to put this on the radar and remind you of the deadline. Okay, let's review. You've already seen annual series. Remember that a uniform annual series is something where the amounts are the same in each consecutive year. And our standard notation for a cash flow diagram on an annual series is that if we're converting it to a present amount, P, the annual series begins the year after P. And so if you ever have a cash flow diagram where there's also an arrow up at 0, that wouldn't be part of the annual series. You'd have to treat that separate from the annual series. The annual series begins at the end of the first year, so here at 1. So we've seen annual series before, and you know that if you wanted to find P, remember here with the dashed line and the question mark, it's saying P is unknown. If you want to find P from A, you simply multiply it by the factor. And you can calculate the factor with the equations or with the factor tables. Those factor tables are at the back of your textbook. And I've also posted just this morning some factor tables on Blackboard. So if you ever find yourself studying and you don't have your textbook handy, it's possible that the interest rate you need could be in those factor tables that I posted to Blackboard just this morning. So if you are trying to find A given P, so now we have these dashed arrows with the question mark indicating that we know the present value, and we're trying to find consecutive equal amounts such that at the end of the last year, all of the money is used up. So this is kind of like a real-world example here. You deposit some money now. How much can you take out at the end of each year so that with the last withdrawal, you've completely exhausted the balance of the account? And so when we have interest rates and compounding, it's not simply going to be divided by n, but you have to look up the factor. All right, so conclusion, P is one period before the first A value. So here's what those factor tables look like, and Jonathan mentions that you can find them online. If you Google interest rate tables or interest rate factor tables, there's a lot of resources that you can find. And so we have factor tables for find P given F, find P given A, find F given P, and so on and so forth. But one of the factor tables that you'll see has G, and G means gradient. It's a little bit tricky, and we're going to talk about gradients today. Before we do, let's refresh our memories about future amounts. So in this illustration, it's showing that the future amount, when you're trying to translate between an annual series and one lump sum amount at the last period, that it happens to be in the same period as the last A. And so it's a little bit strange, but this is sort of like if you took out a certain amount of money every year for 5 years, then how much would you have to pay back at the end of the 5th year to be economically equivalent? And you're paying back at the exact same moment as you're taking the last withdrawal. A little bit odd, but that's the form of find F given A. And likewise, if you are given F and you're finding the equivalent annual series, the F is in the same year as the last amount. So just a quick change of gears. Let's consider a real-world example here. Let's say that an engineer is making a modification to a factory, and that change is going to save $10,000 a year compared to previous expenses. And so here where it says will save her company $10,000, that's not talking about making a deposit of $10,000 each year. Remember, this word save has two meanings. It can mean that you're depositing money into an account if you're saving money that way. But if it's compared to a previous expense, then we treat that as an inflow. We've talked about this before, how if you used to spend a lot of money, for example, on insulating a warehouse, on heating a warehouse, but then you put in insulation and now your heating costs are lower, then the money you no longer spend on heating is counted as a new revenue. So this is one of those type of cases where they made some change to the factory. Now they don't have to spend as much money as they used to. So what we want to do is find out if we have an interest rate of 8% per year, then how much is the savings lump sum amount in 7 years? So it's kind of like the economic equivalence in the 7th year of 7 equal annual inflows of 10,000. So being able to translate a statement in English to a cash flow diagram is an important skill, and of course there is always going to be a way that the statement could have been made more explicit, but all of the information that you need is here, and there's no ambiguity about what it's supposed to mean. It is supposed to mean this and nothing else. So there shouldn't be an amount at year 0, for example, because the change was made, and then the savings that comes from that change is at the end of the first year of operation. So that's why we don't have a 10,000 at year 0. And when it says how much will the savings amount to in 7 years, that's not simply 7 times 10,000, because it says earlier in the statement here, I equals 8%. So we want to find the economic equivalence of these annual savings as a lump sum. So you'll notice here is the factor column that we'd use for this problem. Here's the F/A column. So that means find F given A. And if we go down to row 7, you'll see here's the factor 8.9228. What that means is that the future value is 8.9228 times the annual amount. So remember, when we're moving money to the future, it's compounding. So it's going to be more than 7 because there's 7 of them to begin with, but then like this amount from year 1, to get it to an equivalent amount in year 7, it's going to be compounding and earning interest. It's kind of like you put this amount in the bank and it compounds for 1, 2, 3, 4, 5, 6 years. Then you put this amount into the bank and it compounds 1, 2, 3, 4, 5 years, and so on and so forth. So the solution is that the lump sum value in the 7th year is 89,228. You can see what we did was we multiplied the 10,000 by the appropriate factor and then get the lump sum amount. So it's more than 7 because all those previous years earned interest. Okay, any questions before we move on from this example? Here are gradients. All right, so look at what we have here. This is showing, like, find the unknown present amount if, what if you had a scenario where now at the present you don't have to do anything, and 1 year from now you don't have to do anything, but 2 years from today you have to deposit a certain amount, G. Let's call G is just, maybe G is $100 or maybe G is $1,000, but it just means a certain amount. So let's make it be $100. So 2 years from now you have to deposit $100. Then another year passes, meaning in the 3rd year from today you deposit $200, then $300, and so the pattern is that after each additional year you have to deposit more than the previous year by a factor of G. So it continues to grow until the last year, to the nth year. So a gradient is, we want to find the equivalent present value of this odd, growing, increasing amount every year, that gradient. So G starts at the end of year 2. The first time that you actually see any amount from a gradient is not in the 1st year, it's after the 2nd year, because what we say is that at year 1 it's 0G. So there's the present, then 0G, 1G, 2G, 3G, and so on and so forth. And so what that means, since 1 year from now doesn't have any effect from the gradient, that when you see a gradient starting to form, you have to go 2 years before that, and that is considered the present. The present is 2 years before the gradient actually starts kicking in. All right, so these can get a little bit mind-bending, but everybody here has what it takes. If you've been through calculus, you can figure out gradients. All right, so let's open up the in-class exercise for today and take a look at what we've got. So here's the interest factor that you've seen before, and it's also available on Blackboard. Here's our 8% table, and just to get us warmed up, I'm going to push you into the breakout rooms just for this first one. So it's going to be a short breakout room opportunity. How much is the annual repayment for this problem that's described? So let me pause the recording, put you in the breakout rooms, and then we're going to come back together to work on this first gradient problem. So just give me 1 second to get these breakout rooms. We're coming back here. Alright, so let's look at the solution here. Remember, my earlier suggestion is I think it's a good habit to write the variable right next to where you see it in the problem statement. So this one's easy. I equals 0.08, n equals 8, and it's saying an annual repayment, so we don't have to worry about any kind of conversion between monthly periods and so on. So n equals 8. Now, it's saying if you give a $7,500 loan, it doesn't necessarily say that the loan is at the present, but that would be the default assumption, is that the first time something happens, like some sort of an exchange, is by definition times 0. It's the present. And so P equals 7,500. And then how much should each annual repayment be? So A equals question mark. All right, so let me bring my solution over to the screen. Oh, that's not the one I want to show you. All right, so P is 7,500, I is 0.08, n equals 8. So if we summarize that in like what goes inside the parentheses, this is an A/P problem. Find A given P, and you have to get that in the right order. If you called this a P/A problem, the issue would be you'd go to the wrong column and get the wrong factor. So if you said that this is a P/A problem, then you go and get this factor, and your answer is totally off. That would be a fundamental error, and you'd lose a lot of points. So you need to be pretty careful about making sure that you set this up according to our convention for in the numerator is the unknown, in the denominator is the known. Okay? So here our factor that we're going to use for the A/P is 0.17401. So we write all of those digits down on the page. We use all those digits in our calculator. We don't round off, not yet. And if you multiply that by P, you get A. So A is P times the factor. And so your calculator is going to say 1,305.08 cents. But for complete accuracy, we have to round off to the same number of significant digits as we had in our factor. So our factor had 1, 2, 3, 4, 5 digits, which means we can only know accurately 1, 2, 3, 4, 5. So 13.05 and 10 cents is what we would say. Each repayment should be 13.05.10. Aaron asks, so our answer could be more than that if we found, just popped off my screen, if we found a table with more digits. Yeah, that's right. So you may have a factor table that has more digits. So our answers could be a little different, but still correct. Yes. Keep in mind, the grader is going to be using the factor tables from our textbook. And I don't think very often there would be like a big deduction. I'm thinking more in terms of exams. You know, like if I give you a factor table on an exam, then I would expect you to round off. And if you didn't, I'd maybe give you a minus half a point out of 10, just because I've driven the point home in our class meetings. On a homework, it probably won't come up in terms of points being deducted. But Aaron makes a good point that you could have a more accurate factor table. Okay, so that was our first problem. Any questions on that in-class exercise problem 1? Okay, now this is where things get a little bit tricky. Gradients. Okay, so I'm trying to step you through this. I've thought and I've adjusted this in-class exercise over the years in a way that I hope is going to draw your attention to some of the key points I introduced earlier. Okay, so we're not going to go to the breakout rooms for this one. We're going to work through it together. But what I'd like you to do is, first of all, write the years on the cash flow diagram. Here's the cash flow diagram, but you'll notice I don't have the years on it. So, seems trivial, but I hope that by writing the years, you're going to see what we know about gradients. Okay, so let me pause for a second while you write with a pencil or a pen right there on the paper, what are the years that you need to see. Okay, so 0, 1, 2, 3, 4, 5, 6. And so, first point, even though the cash flow diagram has these tick marks continuing on after the gradient, so you could write 5 and 6, but that doesn't mean that n equals 6 for this gradient. N equals 4 for this gradient. That's the second question here, is what's the value for n and what is the value for g? So even though your cash flow diagram may continue on beyond where things are actually happening, that doesn't mean that the gradient or the annual series continues with the empty tick marks on the cash flow diagram. So n is 6. Now what about g? Anybody know what g is in this gradient? Three. That's a good guess, but it's not correct. Aaron says 200, Cameron says 200, yes. So n equals 4 because it's 1, 2, 3, 4. So n is 4 and g is 200. So g is the amount that increases by like a steady increment of that amount with each subsequent year. So here at time 1 is 0g, here at time 2 is 1g, here at time 3 is 2g, and at year 4 is 3g. So n equals 4, g equals 200. So now that you know that, here's our 8% table. So 8% interest, and n equals 4, and we want to find what is the present value. So find p given g. So in other words, what it says here, use the p/g column in the 8% table. So find the present value. Okay, so here's the p. Cameron asked, will g be linear like this? Yes, by definition, it will be linear. All right, so the p/g column is here. We go down to row 4. So here's n equals 4. Okay, so our factor 4.6501. Now I am going to get to the solution here. Okay, so you'll see, for instance, that I wrote the numbers on there. The reason why I wanted you to write the numbers is just so you could have that kinesthetic reminder that the first time you see the g is in year 2. I said it before, and I showed it to you before, but hopefully by writing down the numbers, like you're interacting with the cash flow diagram in a way that helps you to retain that lesson, that g doesn't start in year 1. The first time you see the g is in year 2, 2 years after what we're calling the present, times 0. Okay, so here's our factor, 4.6501, and now find the present value. Okay, so that's going to be 200 times that factor would tell us the equivalent value in time 0. So 200 times this gives us p. Okay, so 200 times 4.6501 means that the present value equivalent is $930.02. Let's see, did I round off appropriately there? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I did. Okay, so in other words, if you put $930.02 into a bank account now, and the bank account pays 8% interest, then what you could do is you'd have enough in that account, and it's earning interest each year, you'd have enough in that account with a lump sum deposit now to withdraw 200 at year 2, 400 at year 3, and then with your final withdrawal of 600 in year 4, then the account would be empty. That's the economic equivalence of that gradient. Now, why would you need to do that? Who knows? Maybe you've got expensive tastes, and every year you need to spend a little bit of more money to keep up with your evolving tastes in caviar or whatever it is you're spending this money on. You know, what about find the future value? Let's refresh our memory. What does an f/g look like? Did I show you the form of an f/g? Well, it's the same basic idea with find f given a, where the f is in the same year as the last time you see the amount. And so what that means is we want to find the future value as a lump sum in year 4. In other words, if you were going to take 200 in year 2, 400 in year 3, and 600 in year 4, what would be the economic equivalent amount of taking just a single lump sum at 4? That's what we want to find here in question D. So use the f/g equation. Oh, now here I'm saying that you shouldn't use the factor table, but you should use the equation. Let's see what that equation looks like. The f/g equation. So find f given g. So f divided by g is this. Now I'm going to stop for a second and allow you to calculate that factor if you haven't already. Remember that n equals 4 and I is 0.08. So calculate this factor, the f/g factor. I guess the reason why I had you calculate it is that it's not on this table. We don't have an f/g column on this particular table, so you have to use the factor. Cole has calculated that. Let's see, 6.3264. Yes, that's what I got anyway. Can anybody else verify for us? Hopefully Cole and I didn't make the same calculation mistake. Rebecca's got it. Okay. Jonathan gives us the thumbs up. Thank you, Cameron. All right, let's look at the solution. So here's a thing. So I write the equation, and then I write the substitutions, as you can see. And then below that, what's this? I don't even know what that symbol's called. Some sort of a bracket or whatever that is. The point is obvious. You can see what it means. It means that the result of everything in this first term is 56.3264. And the reason why I do that is, like I mentioned earlier, I think on Wednesday, it's a good idea to triple check your calculations. And in doing that, if you write kind of the intermediate quantities, then you get an early validation that you're on the right track. So, if you write this down and you're crunching the numbers and you write 56.32, then when you're coming back through it the second time and double checking your calculations, you'll see, all right, I got the result of this first expression and it's 56.32, everything looks good. And so, if you didn't write this on the page, maybe you slip up and you write the wrong thing on your calculator and then you have the wrong thing in the end and you don't exactly know where the mistake was. But writing these intermediate quantities allows you to find your mistake earlier. We're going to have some problems that just have so many detailed calculations, they just go on and on and on. that this habit of being really explicit with your substitutions will help a lot. And you got to trust me. I've been doing engineering for a while now, and it's worth the extra graphite in your pencil. It's worth the extra lead out of your pen, and the extra paper, the extra space. Take the time to write it. So that little soapbox lecture is finished, and our future value, if we multiply 200 by the factor, then the equivalent lump sum in year 4 is $12.65 and 28 cents. So if you wanted to just get one big lump sum in year 4, the economic equivalent amount would be $12.65 and 28 cents. So that's the basic idea of gradients. You've tried one now with me. Now I'm going to ask you to consider this. It's a gradient and an annual series, both at the same time. It's an annual series and a gradient, because look, there's always 400 every year, but then year 2 it's an extra 30, and then an extra 30 beyond that at year 3, and then another 30 at year 4, and another 30 at year 5. And so what I want you to see is, looking at this cash flow diagram, I want you to look at that and see something else. I want you to be able to know at first glance, oh, I could split that apart into the equivalent gradient. Let me just keep zooming in here. The equivalent gradient and the equivalent annual series. And so do you see how, boy, that didn't scan great, did it? That black and white with the gray in the background. Hopefully you get the idea though. Here's the combined cash flow diagram, but that's the same as a gradient cash flow diagram plus the annual series cash flow diagram. So what we can do is find P given G and find P given A, and then add them together. The combined P would be then this present value, the present value of the gradient, plus the annual series. Does that make sense? Joshua, you got it? All right. So I am going to push you to the breakout rooms. What you need to do here is use the factor table, the equations, not the factor tables. I ask you to use the equation formulas, not the factor table. So you're going to do a find P given G and find P given A. So here's the formulas for that. P given G. Oh, look at that one. All right. And then P given A. Here we are. Okay. But that P given G, that's Harry. All right. So I'm going to push you to the breakout rooms, give you some time to work on your own, check with your classmates if you like. We've got 11 minutes, so I'll bring you back into the main room with 2 minutes to go, and we'll look at the solution together. All right, so what we're trying to do is find the present value of this gradient. And my suggestion is the easiest way to see the steps you need to do is if you write the 2 separate cash flow diagrams. So the 2 separate cash flow diagrams is one gradient diagram where G is 30, and you see the first evidence of it in year 2. And then the annual series cash flow diagram where A is 400 is each year from 1 through 5. Okay, so find the present worth of each of them individually using the equation method. And so the first thing we have to do is find the factor for the P slash A. And you can see how I made those substitutions, and then I show the result of the numerator part of it, the result of the denominator part of it, and the little dot, dot, dot just means I haven't rounded off yet. I'm leaving all the precision in my calculator, so I have a nice accurate factor that's going to allow me to answer to the nearest penny. So 3.60477 dot, 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 which means the present value of the annual series component is $1,441.91. and then the present worth of the gradient. Now here's a long one. Two different terms, a numerator, a denominator, exponents. It's easy to screw up and write n for that one instead of 2 because we get in the habit of n everywhere else, but then this one is squared, so you really got to be attention to detail for a technical career. Attention to detail for sure. So we calculate the P to G ratio here, and that ratio, the factor should be 6.3970, and if you multiply that by the value of G, 30, then the present value of the gradient is $191, and so then in conclusion the total combined present value is $16.33 and 82 cents. Alright, so that's gradients. We're going to do more of them through the semester. We'll revisit this topic on several occasions, but until then, you have a homework assignment to keep you warm. Yes, I'll bring it back up in just a second. Remember, homework 3 is due Wednesday of next week, so that's a little bit sooner than some of the previous turnarounds. So get an early start. That's it for now, everybody. Hope you have a great day. Take care.
Thank you. Have a good weekend.
Bye. You too.